Gabriele is a sociologist, and he holds a PhD from the Hong Kong Polytechnic University, and he was a postdoctoral fellow at the Institute of Ethnology, Academia Sinica in Taipei. He's currently a postdoctoral researcher at the University of Bergen, where he's part of the research project Machine Vision in Everyday Life. Gabriele's work is grounded on ethnographic engagement across multiple sites, and it focuses on digital media practices, socio-technical entanglements, and vernacular creativity in the Chinese-speaking world. This lecture is part of a public program of events here in my open studio at Entrée. In this open studio, I have invited Gabriele and other guests and audience to take part in unfolding themes in my PhD project Unmaking Abstractions that is now coming to an end. In this artistic research project that I have worked on at the Faculty of Art, Music and Design at the University of Bergen, I've been examining abstraction in 3D modeling, and I'm very grateful that Gabriele accepted my invitation to delve into abstraction and parametric design together with us here today. It will be possible to ask questions both here and online after, so you can just write your questions in the chat, and then we'll get to those after the lecture.
Yes,
yeah.
I will.
Okay.
So, thank you, Magnhild, for the introduction. Welcome, everyone. I hope this works. If there's any problem with the audio, let me know. And yes, so I just want to say that this has been very fun to prepare. And I haven't seen Magnhild's exhibition yet, so it's not as much as it's not at all inspired by the works because I haven't seen them, but I talked with Magnhild a bit about her practice and I've seen processes and things. So I hope this will be interesting for you to think through these kind of issues and maybe, yeah. So I built this talk as kind of, I'm going to go through a very difficult text, but hopefully I'm just going to give you some ideas that then we can discuss, especially about these three terms of algorithms, parameters, and models. So yes, this is the title of the talk. So yes, so I don't remember when it happened, but months ago, I just met Magnhild while I was getting a coffee around here. And she asked me if I knew some reading about abstraction. I don't remember how we ended up talking about this. And I just thought of this book by Luciana Parisi, who's an Italian theorist. And it's called Contagious Architecture. Came out years ago. And I read it, yeah, also maybe 5, 6, 10 years ago. And at that time, I found it very difficult to grasp. And but I thought of this book and I said, yeah, you should check it out. And then eventually it became that I went back to the book. And this talk is kind of a walk through this book and a couple of other ones that helped me along the way. One is Aesthetics After Finitude, which is an edited collection discussing aesthetics after computation breaks this limit of human finitude or of the finitude of calculating things. And other books like this one, The Everyday Life of an Algorithm, which is more sociology, anthropology, looking at how algorithms impact our everyday life, which is closer to my own interest and research. But we're going to be talking mostly about the first book, and all the references that I don't say, it's Parisi, it's her. So whenever I'm citing someone without a name, it's from the book, which is also on the shelf. I guess after we can, if you're interested, you can look through it. So this whole talk is kind of framed in this infrastructural turn, at least in sociology and humanities and social science, which means that inspired by books like The Stack by Benjamin Bratton, it means understanding this idea that computation, so everything from my computer to smartphones to cloud computing and servers and Wi-Fi, everything we use today becomes planetary in scale. It's not just one thing, but it's a planet-wide stack of things that interact with one another. And so that's why I think of computation as as infrastructures that are stacked layer upon layer, just like transportation or water pipes or electricity. Computation is another infrastructure. And if we think of computation as a mega structure that spans the whole planet, pretty much, and that comes together accidentally, it's not planned by a single person. Maybe Elon Musk would like to do it, but it's many people that contribute to it. Then to understand such a big thing, such a huge structure of technology, we need to abstract into certain things, smaller components or ideas. And I thought three of these abstractions are algorithms, parameters, and models that I'm going to talk about today. And I think they came up in discussions with Magnhild and in general around art and aesthetics. So I titled the lecture today on infrastructural abstraction, which is a very difficult term to say, I realize now. And what I mean by it is a process by which the stuff that supports computational assemblages becomes abstracted. And by abstracted, I mean less legible, more opaque, simplified, hidden behind interfaces. So one example would be an algorithm is an infrastructural abstraction because you say, oh yeah, the Facebook algorithm does this, but you're making, or everyone is making what actually happens less understandable. You're just putting this word, the algorithm there, and it's hiding everything that happens behind the infrastructure. So this is why I think of these terms or concepts as infrastructural abstractions. And there are two similar related concepts developed by other people. One is infrastructure abstractions. Abstraction is a term it's a technical IT term, which means to think of infrastructure beyond the hardware. I think tech companies use this term, and IT developers use this term. Another one is infrastructures of abstraction, which is developed by a couple of authors to say that in general, computer science education, so programmers, people who learn how to code, what computer science education does to them is abstracting things like, especially like politics and ethics. So computer science education also abstracts things and says coding, programming languages are just tools, and you use them to do things, and you don't need to worry about how they will be used or what kind of politics they have into them. So these are two similar terms, but that kind of inspire me to come up with this one. Now, a step back about abstraction, which is, I guess, if the audience is, or you're mostly coming from aesthetics or arts backgrounds, you probably know way more than me. But abstraction is quite interesting as a term because it has many, many uses across disciplines. The etymologies, of course, is from Latin, and it means to withdraw or to draw away or to remove something from something else. In philosophy, abstraction is a key thing that philosophers do to come up with a concept. You need to start from experience or thought or reason, but abstract into a concept. In computer science, abstraction is an actual thing that computer scientists do to decide which information, which data is relevant to a piece of code. In abstract art, is a key creative strategy. You abstract from a landscape or from an object or portrait, whatever. And here I'm quoting Magnhild from a piece of writing. I forgot when it was from, so I didn't put the date. But abstraction is both a process and the result of this process. So something is extracted out of something else, and the result of this process or action is an abstraction. So you could say abstraction is both a verb and a noun for the result of the verb. And here, and from the book Aesthetics After Finitude, I think it's quite interesting that abstraction becomes a key aesthetic creative strategy for this new kinds of art, because it allows you to understand the creative act as an ongoing, open-ended process and labor. So abstraction was, of course, key for abstract art, but I think is even more key today in new kinds of parametric or conceptual work. So getting to Luciana Parisi, her understanding of abstraction is mostly based on a philosopher called Alfred North Whitehead. She's a philosopher, so she writes about 90% about philosophical debates, but of course these are connected to aesthetics and architecture and creative practice. But basically she draws on Whitehead to say that the aim of speculative reason is the production of an abstract scheme. So using thought, speculating about something is the main goal is to produce abstraction. And in fact, Whitehead says abstract speculation has been the salvation of the world. So if philosophy to us is abstraction, is what it contributes to existence probably. But for Parisi, this philosophical starting point is then useful to think about computation, because she says, okay, we need to use this idea from philosophy to talk about computation, because computation is also the production of these abstract schemes. And to do this, we need to understand that computation is not just zeros and ones and putting an input and getting an output, but there's something more that's similar to how reason thinking works. And she does this through a few main concepts of computer science that I think we can go through. One is that of abstraction itself. This is a representation of what computer scientists think of as abstraction. So if you start from the very basic thing that computers do, which is compute zeros and ones, at least the digital ones, then what computer scientists and programmers and developers do is abstract things so that us, the users, can use the computer, because we wouldn't be able to do anything with that. So you start from the machine code and you abstract into higher level assembler languages, procedural languages that you can actually type and learn as a human. You have object-oriented languages that you don't even need to learn coding much. You can just move stuff around and do more complex things. And then you end up with things that us can do, like apps or dragging stuff around. And this is actually, in computer science, a process of abstraction that moves in time. And which means, according to Parisi, that algorithms, so things that calculate stuff at every step of the way, are both actual and abstract. So they, of course, exist in time and space, but they're also abstract and are capable of determining changes in our lives, in things we do, in every decision we make with our digital technologies. So this is one conception of abstraction that she uses quite a bit. Another thing she references quite a lot is the Turing machine. This is a representation of one possible format of the Turing machine. But for her, the interesting thing about the Turing machine, which is a very early idea of a computer able to calculate anything you give it, it's that the Turing machine is a model of an abstract machine. So it doesn't need to exist. It can be created in many different ways. It's not a design of a specific thing. It's more of a concept, an abstraction. It's a model that can implement any algorithm. So the point of a Turing machine is that it can calculate anything that is calculable. And for Parisi, this kind of machine, the Turing machine, proves one thing, that is that there are fundamental limitations to computation. So one key thing that interests her is that computation is not super powered, is not like omniscient, I can do everything. She's very interested in the limits of computation. And the Turing machine is, for her, a great example of this. Another thing she references often is this idea of cybernetics and first order and second order cybernetics. And cybernetics is just this line of thought that has been developed for decades and decades, since the 40s and 50s. And it's a very simple idea of loops. So you input something and you process it, and then the output comes out, and you use the output to, you feed the output back into the input. And this is a very simple first order cybernetic loop. And in the second order, they just added an extra loop in which, yes, the output comes up, and then you reflect on the output and again, input it back into the thing. But without going into details, what interests her about cybernetics is that it allows to limit computation into a single loop, and then break out of it and criticize in which ways abstraction exceeds this kind of thinking of just limiting computation in a single loop. And this is very clear in one term that we discuss a lot today, this idea of a black box. So when we say algorithms are black boxes or platforms are black boxes, that, you know, we put our data in, something comes out, an advertisement, I buy a sweater, it's because the algorithm knew me. And I'm just an observer outside of this loop, and I don't know what's going on. She actually traces this idea of the black box to Alan Kay, who's a mathematician and computer scientist who kind of invented the laptop decades ago. And he already foresaw how algorithms would become this kind of abstracted background objects that can adapt, change, and evolve in our everyday lives. And you know, if today we discuss black boxes in these terms, it's also because of this longer history of the term and of cybernetic ideas about computation happening in this, you know, black boxes of not understandable for humans. And lastly, another concept that she discusses a lot is cellular automata, which are this kind of graphical representation of very simple rules that can create things that are seemingly alive out of code, or patterns that are, visualization of abstractions that develop randomly, depending on what kind of seed you give them. And for her, this is another kind of ideal of or abstraction of computation. It's this idea that through computation, you can obtain something as complex as life from something as simple as a tiny bit of code. And all these things are things that she's interested in, but also criticizes. So that's just to make sure you kind of get a sense of all the reference when she discusses more complicated things. So the main conceits of this book, called Contagious Architecture, are abstraction in computing. So Parisi wants to understand what is abstraction and how it is related to computation. She's interested in how algorithms contaminate reality. So that's why she talks of contagiousness, which is not a great word recently, but she didn't know this. So her meaning of contamination is actually very practical. So how do algorithms influence you? It's not necessarily a one-on-one relationship. Algorithms influence reality in a way that you cannot understand on a large scale. Think of even just contact tracing epidemic systems. Even if you understand how the algorithms behind them work, you still have no idea of how to understand the social effects on a large scale. And she understands this in terms of contamination. Once you put an algorithm, a tiny bit of code in the world, it will spread and have effects that you can't compute. And she's interested in the limitation of computational logic. And she kind of moves against the closed nature of cybernetics and this proliferation of discussion about black boxes. And she's also critical of this idea of creating complex forms from simple rules, which is probably also related to the kind of parametric design that we will discuss later. So these are the main ideas of the book. And how she does this is moving three critiques. And the first one is against what she called the double fallacy. So the double fallacy is this idea that there are that algorithms are either finite and black boxes and cybernetic loops, or that there are generative, simple piece of information that create complex life. So the two things I just presented. She calls this a double fallacy because it's not, computation is not either or. Thinking that it's either or, it would be this double fallacy. And how she moves beyond this choice you have in understanding computation is to say that what is missing is re-understanding the role of quantity and of the infinite into algorithms. To make this wall of text, which I could not make shorter, simpler, this point is basically that if you want to move beyond understanding, computation is either loop or complex from simple. You need to rethink about the role of the infinite and infinite numbers and randomness. Because, as she says, in algorithms, there is always an extra, or in computation, there's always an extra, an uncomputable infinite, an extremely large number, randomness that you can never know how to expect or prefigure. So, so that's her main point when she says we need to go beyond this fallacy. Her second point is to move beyond cybernetics, so beyond the loop. And to do this, she uses this idea of the incomputable, which is what I just described, this infinity, this very large numbers or random numbers. And she draws on this mathematical idea of the omega, which might be the next COVID variant. But the omega in mathematics is just a number. It's quite interesting. It's a number that represents the probability of a program to fail or stop at some point of a random program, computing program. So it's not a fixed number. Omega is not like pi 3.1.4. Omega is a fluctuating number, but it's always the exact probability that a piece of software will fail. And so it's a real number, but it always changes. And this mathematician, Shaitin, says that when we think about algorithms and computation, we need to think about this number that is always at the outside of computation. It's incomputable. And it kind of embodies those chaotic parts of information that cannot be computed. Her way of moving beyond cybernetics is through this attention to the thing that cannot be computed, the uncomputable. And the third point, and it's going to get easier after this, I promise, is Contagious Architecture. That's the title of the book. And what she means by this is that this contagion of algorithms is impacting everything in the world, and because computation is a mega structure and it's everything around us, algorithms structure our worlds, and that's what she means by architecture. It's not just the practical making a building, it's how platforms are created, how software are structure a way of doing things, our social security infrastructures, social networks, our social infrastructure. What she means by architecture is practically how algorithms build these worlds around us. Or, as she says, the irreversible invasion of incompressible data into the digital design of space. Incompressible data, here she means that point two we just discussed, the incomputable. So when the incomputable, omega, comes into our world, it influenced the design of space. Here, I think Magnhild's work, some of it is quite, we're just discussing these objects that were scanned and then 3D printed. And I think in this, it's extremely evident how this impacts architectures. We can discuss this later, but this is precisely the entrance of incompressible data into digital design. And that's what Parisis is quite interested in. And the last step is that she says, okay, this contagious architecture exists. How is it useful for thought? How is it useful for philosophy? Why is it this interesting? And her answer is, that algorithmic architecture becomes a meta model of algorithmic objects, which are conceived as discrete entities imbued with infinity. So what this means is that once you work or you start working with algorithmic architecture, you create an object, then that object in turn is a model of the algorithms, of some algorithms, or of how algorithms work or not work. And so algorithmic architecture allows you to visualize some of these issues. It's a tool for thinking about algorithms or computation in general. And that was the first part. Now, what she does in the book is not just philosophy, but she also discusses quite a lot of examples from architecture and art and design, and what has been known as parametric architecture, parametric design. She discusses things that precede parametricism. Oh, this is not 2004, this is 1997. For example, these are some walls made by the Milgo Bufkin studio, in which sheet metal walls are created through just algorithmically generated geometry. So there is no design process here. It's just an inputting of geometrical parameters and then letting a machine cut the metal into different walls. So this is kind of the most basic example of contagious architecture for her. And she also analyzes things that are directly connected to code. For example, this is called Cellular automata. It's also a kind of architectural plan directly derived from the cellular automata we saw before, so generating complex forms from simple code. And this shows how the development of design and architecture has gone in parallel with developments in informatics and computer science. This is literally just the application of cellular automata to architectural design. And she uses these examples to show how precisely that code and algorithms are malleable and can be, yes, abstract, but also physical, very real, when you can realize surfaces and structures that reveal the incompleteness of form. So going back to the incomputable and this similar kind of objects. She also analyzes the emergence of more interactive forms of design. This is an installation by United Visual Artists, I think, volume. This is also parametric in a way because it's an installation with lights and music. I think it was done by Massive Attack as well. And the point of this installation is that people walking around it become part of the control system of lights and music. So their movements kind of shape the installation in different ways. And she uses this example to explain how users don't need to understand algorithms. All they need to do is to experience it and walk around. And this is precisely how things become abstracted when you are the control point and the environment reacts to you. So her writing is quite interesting in how it combines deep philosophical speculation with examples drawn from architecture. This is a pavilion for Korea, I think an expo or a biennale, that she uses to also explain how this sort of new parametric architecture uses or kind of welcomes visitors as passive entities that are part of the design. And this pavilion has a similar thing to the previous one, in which as you move around the structure of the space, the lighting changes and the structural beams shift subtly to restructure the space around you. And this is all, again, designed through generative algorithmic design, but it shows how these algorithms are infectious or contagious in that they change space around you and kind of use you as a variable or a parameter in the development of space. And this kind of architecture has become increasingly popular today. I mean, my university in Hong Kong had a building by Zaha Hadid, which was 100% parametric design. And this was the Taipei Performing Arts Center proposal. I don't think this one won it, but it was a proposal entirely based on this like parametric structures that are quite easily identifiable because they look definitely, you know, not human or not computable by human designers, if not with a lot of effort, but effortlessly computed by these kind of systems. But overall, the book discusses this kind of projects or designs because it is interested in seeing how algorithms and computation reshape the geometry of existing architectural practices. So there is a whole space of architecture that we could not access without these sort of systems. They can find new spatial architectural configurations that work, but you can only know or reach them when you delegate the design and structural solidity to a computational system. And that's why she focuses so much on this kind of architecture. Yes. Now, as for the provocation part of my talk, which is the third and last part, I wanted to just talk about three specific infrastructural abstractions. So the first one is the algorithm. We mentioned it quite a bit. And it's interesting that the algorithms today are such a huge buzzword and keyword, but in, you know, they're a very simple thing. They're usually understood as like logical flowchart. So you start here, you do this, does it work? Yes, no, keep going or stop. So just, you know, a loop of instructions. Or as a set of rules in coding. You think of an algorithm as, okay, if this happened, do that. If not, do this other thing. That's an algorithm. It was not that popular or fancy 10, 15 years ago, but today is basically the abstraction through which we think about everything in our lives. In the book, The Everyday Life of Algorithms is quite interesting because the author examines the everyday life or the life of an algorithm designed to identify passengers or their luggage in airports and stations, because we never think of what an algorithm is. And this is that algorithm, as the scientists and computer scientists who were developing it wrote it conceptually. So that's the actual shape of an algorithm. And then this algorithm is fed into more complex computing systems. It's just one part of them, alongside cameras and servers and terminals and all that stuff. And the result is that you get computers to see and abstract away from reality the shapes of people or the shape of luggage. And it doesn't always work. And as Daniel Neeland, the author of this book, says, the algorithms and the systems don't operate exactly or entirely in line with what you expect them to do or with parameters that instantly make sense. So algorithms might do what you designed them for, but there's always this uncomputable or unexpected results. Sometimes they might identify someone's face as a luggage, or sometimes they might identify a luggage as someone's body because of their position. And I think there's a very good example of how when we think of algorithms, we often just abstract away. But in fact, once you look into how algorithms are developed and what their role is, it's very easy to start seeing the effects of abstractions or the effects of uncomputable data on our lives. And perhaps the most visible example of algorithm today is Facebook algorithm, or this is how Facebook talks about their algorithm, but every platform has algorithms. So how Facebook explains the algorithm to you, the user, is through this kind of algorithmic imaginary of a funnel that sucks in all your data, makes an inventory, and then through different models that you don't know how they work, it structures into a portrait of you, and according to this portrait, it gives you the top relevant post you want to see, or gives scores to your friends to show them your picture, their pictures or something like that. So it's very easy to see how the everyday life of an algorithm and what a platform tells you about the algorithm is quite different. It's abstracted in very different ways, and I think it's often we talk so much about platforms and algorithms that we forget that algorithms play a role in a lot of other things, including 3D printing, for example. And I read a bit about how support structures are generated. We can see a bunch of them in those models. So when you print an object, it would be impossible to 3D print an object without support structures, because the plastic needs to, thermoplastic needs to cool off in shape. And if you don't have superstructure, it will just deform or not work out. And so these support structures are not designed by a human designer. They're generated according to the shape of the object. And what does this support structure is an algorithm. This is one of the papers I read. That's how they describe their algorithm. So you start from a model, you slice it into planes, and then it does two things in parallel and then merges them into the results of these tree-shaped supports. And there have been years of research into which supports are more optimized, if it's a tree structure or individual rods or a matrix of things. I think you can even see the variety in different support structures for 3D printing. And I think this is a great example of what Parisi was saying, that contagious architecture or algorithmic architecture, yes, it's useful, of course, to the 3D print, but also allows you to see the effects of computation in the material, right? You would throw this away after you 3D print it, but this as an object, it is the instantiation of this uncomputable entering our everyday life. So this is what I mean by algorithms as infrastructures of abstraction. As Parisi concludes, this would be this abstraction as the selection of eternal objects by actual occasions, the becoming form of irreducible qualities and quantities. Now, this is a very complex way of saying what I just said about this, but if you read this quote and perhaps try visualize it through these objects, it might now make sense, or a little bit, but yeah. So this was the first infrastructure abstraction. The second one is the parameter. And the parameter, I like to think of it as zooming into the algorithm. So algorithms include a lot of parameters. And today, parameters are extremely important in the training of machine learning algorithms. And there's even such a thing as hyperparameters. But in short, a parameter is a value inside the algorithm, something you fine tune or something you decide or something you let the algorithms change. And it's quite interesting that parametrization is an important part of developing any kind of algorithmic systems. And if you think of the example I just showed you of the passenger and luggage detection algorithm, whenever you pass under a camera that recognizes you, or even around the city, you often don't think of how much work is there to make sure that what the camera sees is a valid thing, like a human or a luggage, because the camera and the computer behind it has no idea of what a human is or what a luggage is. And all it has to recognize it is a mathematical value of pixels, of each single pixel. So in order to have it understand what a human is, you need to write a very complex algorithm or system of algorithms. And to give it very precise parameters, and saying if there is this sequence of pixel, or if you can see this box-shaped thing that moves in this way, that's a human. And even after you do this, it's not necessarily always successful, but this process is called parametrization, which means giving the algorithm the parameters of what a human is in an image, or what a luggage is in an image. So Daniel Nillen in his book says, parametrization for computer scientists, parametrization is a form of classification. So for a computer, you cannot just say, find the human, find the cat, because it doesn't know what a human or a cat is. So you need to parametrize these subjects. So from this, we can see that the parameter, which is just a very simple mathematical concept, becomes a key abstraction through which we understand the systems. And I think since we're here today, the most simple basic example of this is the Bezier curve, which is a parametric curve based on a set of control points, which is how Magnhild designed this space, the shelves and the tables as well, right? So a Bezier curve is I think the simplest example of parametric design, of the use of parameters or parametrization in design, because basically what it allows you to do is to have a curve, to design a curve without having to draw the curve or to come up with the curve yourself. All you need is a set of parameters, like a starting point and ending point of the curve, plus a number of control points. And once you have these, this polynomial process will give you the curve as a result. And this is very basic and has nothing to do with, well, has a little bit to do with computer science, because after Bezier came up with this curve, it was used in the 60s to design cars, Renault cars specifically. That's the beginning of cars having some curves that we still see today, which would be impossible to design or very hard to design by hand. But by using the Bezier curve, you can just move control points and the calculation does the curve. And it's interesting that we still use Bezier curves in, for example, music making, video making, audio and processing. Whenever you do envelopes, if any of you has used any video editing or audio editing software, whenever you create this kind of envelopes or control surfaces, and you're moving a point and the system is generating a curve, that's a Bezier curve you're using. And of course, in vector graphics, graphic design, it's all based on Bezier curve. And that's how you make design that is scalable, that has no pixelation. Is just because all you have is the control points. The computer does the actual tracing of lines. So I think as an abstraction, the Bezier curve is a very good example of how the parameter is the most basic way in which you delegate something to computation. You're saying, I do not draw the curve, which is this infinite set of points. I will just choose 3, 4, 5 points, and you, computer, do the curve, which is this, more than human computation of a set of points. So even smaller than an algorithm, it's just this very basic unit of parametric design. And of course, this has spawned a whole current called parametricism in architecture. This has been formulated by Schumacher in 2008 from the Zaha Hadid studio. But over the years, there has been discussion about the beginnings of parametricism, which can be traced back to the 50s, and early parametric work in architecture that started to think about this continuous geometry, use of sensors, interactive environments that shift around. And today there's discussions of parametricism 1.0, which was the last decade. And then today we have parametricism 2.0, that its theorists say it's parametricism with the parameters that matter. So they start having some social concern and promoting this idea of parametric architecture and design by they can go mainstream and become usable for everyday architectures once we figure out which parameters are actually important for us. And I don't know, but in the future with machine learning, there might be a current of hyperparametricism that develops in the next decade or something, in which even more is delegated to computation of this kind of design. So parameters are also infrastructure of abstraction. And following Parisi, I think it's interesting that she discusses parametricism as this architectural style that uses parametric software to model urban space and behavior by including contingent relations in software programming. For her, what parametric design like architecture like Zaha Hadid buildings embody is precisely this way in which our spaces, urban spaces, are being reshaped by the choice of parameters that we come up, or architects come up with. So if you design a building and one parameter is, the position of the user inside it, it will be a very different building if you focus on the gender of the user or the age, or if you take into account all of these, or if you take light, temperature into account. So for her, philosophically, this is a shift towards a conception of space that moves beyond the human and incorporates new kinds of rationality, and in this case, the rationality of computation and the uncomputable. Okay, almost over. The last one is the model. So the last infrastructural abstraction is the model. Now, I know in architecture and design, that's probably the most common use of models. So making a smaller version of a project that you're up to do, I think those are models, right? We were discussing. But in what I'm thinking here, if we shrank down to parameters from algorithms, the model is actually zooming out and seeing the larger pictures. Because in computer science, models are, especially with the machine learning models today, models are basically trained algorithms or algorithms that are developed into actual systems. That's what you usually call a model. So it is an algorithm that has been fed data, usually a lot of it, and that has outputs. And these outputs have been used to keep training it. And once you're satisfied with the results, you have a model that then you can sell or employ. And the philosophical shift here for aesthetics is that once you have a model that can either create art or evaluate art or write a science fiction story, any kind of machine learning model, you basically have a new agent that can perceive the world in some way. So the question is, what happens, as the Aesthetics After Finitude book says, what happens when perception can start to see itself? So what happens when an algorithm can start, describing itself? And it might seem science fictional, but we have seen actual examples of this recently. For example, with the GPT-2 and GPT-3 large language models, which are precisely these machine learning models trained on billions and billions of text, lines of text drawn from the internet that can then produce text that looks mostly human and makes mostly sense. Actually, GPT-2 and 3, you can ask them about themselves. So you can say, hey, what are you, right? What is an algorithm? And they can describe what an algorithm is. Now, it doesn't mean that it knows, but it's a new form of reason, in a way, that we still imagine as this structure, or we still model as a model, so as an algorithm that learns some things and is trained, but it is in fact a new form of cognition, at least, if not of reason, that we need to take into account. And this is becoming increasingly relevant because these models are, first of all, they are developed by massive tech companies often, and they are used in the platforms that we use every day. And some of them are, then made open source, like GPT, and the parameters on which they're trained determine their outputs. So who gets to choose the parameters, who gets to use these models, and who gets to decide what their best use is quite important for the future. And in terms of design and architecture, this is quite evident in what Parisi discusses, blobs and objectiles, which for her are one of the best representation of models and modeling that shift from being just a model of a structure that you want to build, a smaller version of it, to the model becoming in itself a dynamic process in which you don't design the whole structure, but you actually let algorithms design a component, and then you build component over component, and the architecture grows out of the parameters you choose for the individual component. So this is Blob Wall by Greg Lynn, which she uses to explain this shift of model from something that is kind of a human abstraction of something you want to build, to the model becoming in itself the result of this process of abstraction. And so for Parisi, models are also, no, for me, actually, models are infrastructural abstraction. But I'm drawing on Parisi here to say that these models are, similarly to algorithms, are become actualized in these sort of adaptable interactive spaces that parametric architecture allows us to explore. So today we're here. It's not, it's a very simple parametric design, but we can also experience that modularity and even just shifting the screen around. I think it's a small scale example of how these sort of abstractions infect our actual spaces and structures. So last or second to last slide, I'll just wrap up with some takeaways, which are more abstractions, just to wrap up. So I have started from this idea that planetary computation is increasingly abstracted. Algorithms, parameters, and models function as infrastructures of abstraction. But abstraction is not just a technique, it is a process, and it is the result of this process. And so we need to constantly examine and undo the infrastructural abstraction of computation if we want to understand how it works, because I think it's dangerous to leave it abstracted. And algorithmic architectures, parametric histories, and modeling decisions that I just discussed reveal how things like support structures for 3D printing, or the way we delegate agency to parametric design, or the way models rely on hidden training data sets are central to these vast infrastructures. So in a way, if we think about infrastructure, we need to also think about the structures that are that are inside it or under it. And I wanted to conclude with something from your text, actually, with this idea of unmaking that Magnhild discussed, because I think that the point is precisely to unmake abstraction, or as you say, to picking apart and reassembling things, and to use, in your case, various artistic media. But the point is to unmake, to do so driven by curiosity and searching with an unknown end. And the goal is not just to gain insights that can be concrete and translatable into language or other new abstractions, but perhaps even more importantly, to invoke questions, experiences, feelings, or observations that escape attempts of making such translations. I think this was quite beautifully parallel to Parisi's idea of the uncomputable, what we cannot account for in computation. So I think this idea, this strategy of unmaking abstraction is key if you want to understand and undo the abstraction of computation. So I'd like to leave you with this quote. also from Contagious Architecture. In case you want to go back to the book, I'm still struggling through it, but I think this is a quite beautiful quote to end, also in a hopeful way. And Parisis says that despite all efforts to fuse distinct platforms into one smooth plane of compatibility, there is no ultimate finite set of algorithms, no elegant formula, and no synthetic AI able to compress all data stored and produced in distinct databases. On the contrary, the algorithmic processing of data cannot but face the ingression of incomputable information at the edge of each cognitive act of perception, an ingression that serves to release the aesthetics of computation from its limited conceptualization in terms of a sequence of logical steps, opening it into a speculative function of reason. So it's another heavy quote, but maybe after this hour, it makes a bit more sense. And I'll leave it here so we can have some discussion. Yeah. Thank you. I hope it was not too long. No,
that was perfect. Thank you so much. I'll move over here so I can be seen. Thank you so much, Gabriele. That was such a rich and generous lecture.
Thank you.
Yeah. Does anyone want to ask some questions, either on Zoom or here in the audience? Maybe I'll start with
we can just talk about things.
Yeah. One thing I was thinking about is this starting point. The starting point where something becomes something to generate new algorithms or abstractions. You mentioned the position of a person in a room as one such starting point, and of course there has to be like some input to start generating something from. I was wondering if you could tell me how would that input be, for example, in music, or you've been looking into how this is used in other practices in architecture and design, for example, in music. What would an analogy there be?
Yeah, in music, I think in music there's quite a lot of this, and it's I think there's an increasing, especially in things like live coding music, where you don't even, because of course in music making with synthesizers or even digital things, you are inputting a lot of data. It could be a note or a trigger or a click. So there's always using inputs of the outputs of something to drive something else. So you might use a sequencer to play a synthesizer and then changing parameters on the synthesizer and the sound changes. So this is very basic. But recently there has been a lot of experimentation with live coding music, which is basically you don't use synthesizers or instruments, but you directly write code. So you input numerical parameters that just change pitch and length of a note or any parameter of whatever instrument or synthesizer you're working on or you're creating, but you're just typing code, and you don't see waveforms. You just listen to the output and changing things to shape the sound. So I think this is quite similar to parametric architecture, or to even just simple, designing getting a 3D scan object and then 3D printing it to see what happens. Let's say the only feedback you have is your senses. So you type something, you see how it sounds, and then you feed back into it. I think this is becoming more and more common in many creative practices, because it's very it allows new kinds of experimentation in a way. if you're going down to the most basic form of delegation to your tools. So you don't have to worry about certain practical things to create. And you delegate drawing the curve to the program so you can experiment with the control points. That's the point, I think. Yeah. Yeah.
I'll ask one more.
Yeah.
That's something right there. It was so cool that you had gone into this algorithm that generates this shape here.
Yeah.
Yeah, this thing. Can you tell me a little bit more about what you found out? Because I've worked with it much more in a practical way and in a very unmathematical way, where I looked at the 3D model on the screen and I wanted to materialize it as a larger sculpture, but because the algorithm was proprietary information, it was actually like not possible to materialize it as a larger object. Yeah. So then I went through this very manual process of like translating back and forth between the screen and a physical object. So I'm really curious to hear when you went into this in a more like theoretical analysis, what did you learn about this type of algorithm and how it's made? Yeah, well, what I learned is that there are many, and how it works is that computer scientists work on this theoretically, and they write papers and they present them at conferences and publish them. And there is a whole history of support structure modeling for 3D printing that started from the most simple ones that are basically a column. So if you need to model this candy like this, you just put a lot of columns up. And then this was what the earliest 3D printers did. Until they realized that it doesn't work for some kind of things, then you need a certain spacing, and sometimes if they're too long, they bend. So then computer scientists started to try to optimize things, and that's how they moved between a lot of different kinds. So they started from like this slanted, this one is, I think, it looks like that. Yeah, it's like slanted, parallel beams or pillars with these slanted beams between them. And then from these, they developed into the more tree-like ones that I showed that have like roots and then branches up. And there are other kinds like matrix or lattice-based ones. So this is what the computer scientists develop. But then when companies basically hire the computer scientists to develop a system for them, then it becomes proprietary. Unless they decide to keep it open source. And there are different ones. There are open source ones that you can use if you want, or if you buy a 3D printer that has their own software, of course, you're stuck with that, and then you cannot, you cannot even see how it works. So I think this exemplifies a very common thing in computation today. There is a lot of research that is academic interest that is out. You can go and read it. It's out there, but then it's it becomes a proprietary model, and then becomes hidden and becomes abstracted away from you. And I think so. Probably your impulse to go extract it again from the proprietary thing was interesting to me, because it was it was giving like bringing back this often hidden part of computational design, and trying to make it, to give it presence, making to a sculptural object. So yeah, that's what I found by reading some of those articles. Do we have some questions online? Andreas? No? Okay. Should we just Cameron? Yes, please.
Yeah, I'm a bit confused. I'm trying to grapple with her critiques. Yeah. Yeah. So I've literally read this like 5 times. Yes. When you guys were talking, I have no idea what you were talking about before. I just kept reading this. That's good. I'm not like her idea of like something that exists outside of computational design, right? Is that the critique? Is that like that there's like within whatever tool that you're using, like there will always be things that you can't do outside of the functionality of the system, in which case then you're limited by the tool.
It's not just the thing you cannot do. I think that's of course. I mean, it's like a Turing machine is an abstract thing that can do anything, right? In computational terms. So whatever algorithms you come up with, you could give it to a Turing machine and let it do it, which is what computers do today, right? They can compute anything if you write the right program. But what she's saying is that in any algorithm, in any program, in any formal computation, there is always the chance of failure, which is represented by that number omega that she draws on. And for her, that represents the constant presence of the uncomputable in algorithms. And that's why she critiques both approaches of cybernetics and of synthetic life, because she says those are two idealizations of computation. One is
idealization.
I mean, they're like how you idealize computation. With cybernetics, you say it's a loop, I put it in, comes out, good. And the other one is I put a simple instruction, something complex comes out, that's great. But she says this is not enough, and it's not how computation works, because in both cases, there is always something that unpredictable or something that you cannot compute until you have the program and you're running it. Then you can, see how it fails, but you cannot compute it in advance. So what she's saying is it here? Well, that's why she concludes with this. I think her whole point is criticizing this idea that computation is either omnipotent and all-powerful and we can just rely on it, but also criticize the idea that it is just a loop of instructions and that's it. She wants to say there is something we cannot grasp as humans, and we need to grasp it from the perspective of computation, which is always offset, or there's always the risk of this incomputable information getting in. So that's why she says there is no ultimate set of algorithms, even if today we're in this world where it's like Facebook is everything, we can do everything, metaverse, AI, whatever. She says there's no final model of that we're done, right? There's no synthetic AI that can process everything. There will always be this uncomputable information. There will always be this possibility of failure of programs, if that makes sense.
Yeah, I guess. I mean, I'm just like wondering who these people are that have like this idea that computers can compute everything. It's like who are they?
I think she's criticizing. I think she's responding to. She's responding to a bunch of people, mostly, theories of computation and also popular understandings of computation in general, and just this idea of using technical solutions to a problem. You have a problem, you throw algorithms or you automate something and it's over. What she's saying is maybe it looks like it's over, but there are some incomputable things that until you put it into place, you don't know what the effect will be.
Yeah, right.
So once you put it into place, then you can compute the.
It seems like the savior to that is the feedback loop, right? It's like, okay, like you have a feedback loop that exists with the system, right?
Yeah.
So it's like, okay, but she's got a critique on the feedback system as well. So I don't really, because if you're learning a tool and that tool is immensely complex, it's calculating things that will go way beyond human intelligence, right? Is that you're feeding the system, the system responds to you, you have a result, and then you input again, right? In order to constantly, in order to get the thing that you're looking to get, whatever, right? Yeah. So how does her critique of cybernetics come into this logic?
I think it's I mean, she's not criticizing that the feedback loop exists. I think, of course, and they're good. I think like this example you gave is, I think, a good example of how they, you use them and you work with them, see what happens. But what she's critiquing is the idea that you can theorize about computation through just, the image of the feedback loop, so that you can say, okay, I want to make a system like this. I'll get some data as input, comes out, feed it back, problem solved. Because until you do it, you will not be able to know which other incomputable things will come in. So I think she's critiquing the idea that you have a model like cybernetics, or you have an idea like cellular automata to generate something without taking into account the incomputable information. So the point of omega, which to me is fascinating, but that is a number that this mathematician came up with, which is interesting, because the point is not that it's too big or it's too random for computers. It's just that every program you create will have a chance of failing, but you cannot know what this omega number is before you write the program. So you have to write the program and run it, then you can calculate the chance of failure. So that's what she draws upon for this idea of the incalculable. So it's not that computation is either perfect or will be imperfect, because it cannot compute everything, of course. But the point is that even if the chance of failure is very small, or you can compute it, but you cannot compute it before you do the program.
But there's kind of two different types of failure, right? Like there's one type of failure, which is actual system failure.
Yeah. Right? I think she's talking about the actual.
That's what she's talking about. She's not talking about the fact that I run an algorithm and then
you don't like the output, or whatever.
Or it creates social consequences that
I
couldn't have predicted. She's referring to actually the technical.
So this omega thing is referring to the technical thing, and I think she's using it in both ways. So she's using it even in a more theoretical way to say, the incomputable might just be that you don't know how it can fail when you use it in society. And once you put it out, then you say, oh, this is actually how it could fail. Yeah, I think that's it. Anyone
else?
Oh, to talk about those.
Do you want to talk about that?
No, I think those were interesting, because for the house or all of them.
Yes. We started a conversation just before your talk, and I was talking about. I was telling you what I did with these objects here on the shelf. Those come from. I work together with Indian mechanical engineer Sirisha Shashikant, and she 3D scanned some objects that she had at her office, where she was working in a company where they had recently bought a laser 3D scanner, and they were training how to use this scanner. So they just took some objects that they had at hand, lying around their office, and used them to figure out how to use this machine. I purchased these models from them, and we 3D printed them at Aldea. And then we used the 3D prints to make silicone molds that are also up here, and cast jasmonite into them. And there's many different things that I was interested in about these objects. One is that these kind of random objects at hand have, in the history of computer graphics, become these standards. But also that the kind of distortions and the fails in the objects show some elements of the abstraction process. And the translations that the objects have gone through, such as, for example, that you can see the polygonal structure in some of them, in the conversion, or in some places even there's a part missing. There's a hole because the scanner missed something, but what made me first start thinking about abstraction in relation to 3D scanning is that, of course, you have a sensor that picks up the only information that it picks up from the object is the form.
Yeah.
So it extracts the form from all the other qualities, such as color, surface texture, smell, taste, the meaning of the object, what it is used for example. So you take this one property out of the object as a whole, and that's what remains, and what can then, because it is abstracted into mathematical information, it can then be used, it can, go in through different technologies and be used in different ways. So this, working with this reproduction of these objects was kind of like an examination of that abstraction process and what it does. And one of the kind of obvious and like a little bit funny things that I discovered in it was that when you, of course, the scale is also something that can very easily be manipulated when it's transformed into numbers or XYZ coordinates. So when we rescale these objects to fit the printer, 3D printer, then they become very they have a very floating scale in relation to each other. Like the computer mouse is like really huge and the hammer is very big. And, So that was like the interest in this abstraction process that I wanted to examine in remaking these works.
What I don't know, I think these are interesting for like the things we were discussing, because in this, like, I don't know this one, but probably in all of them, you can see both abstractions on the same, how they combine. Like you can see the scanner made works with polygons, so you can see that the shapes of the original figure are kind of abstracted into polygonal structures. But then you can also see the layering of 3D printing, which is the filament-based thing. It's more like analog curves. So it's interesting that in a single object you can see both layers, both kinds of abstraction at play, overlapping. And when you look from distance, it just looks like it's a model. But then when you look at it, you can literally see the various kinds of abstraction at play. And I think this is a good example of this idea of incomputable thing, because you cannot prefigure how this will look like. You cannot calculate in advance how scanning it and then printing it will make it look like. You can only know these details after you scanned it. And it really depends on your uncomputable things like your position or how experienced you are with the scanner or what the scale you build it up. So I think there's a very good illustration of these issues, or at least thinking through them.
What was interesting to me is also how actually what the object is, or what function alters when you change the context and remove so much of its attributes, such as the plate up on the side there. When you give file names to stuff, often it's like you just write something, the first thing that comes to mind, and it's like this one had the file name tea sauce plate, and we were all very confused. What's a tea sauce plate? So we 3D printed it and worked with this object for a long time without knowing actually what it was. And
that is something you scanned, or
that was something that Shirisha scanned in India, and then she gave it that title, and she sent me the file, and we were just reprinting these objects from their office. And that was kind of the important part of it, was that they were objects at hand. So I had missed what is exactly this thing. What was this thing? And then we were reprinting it and rescaled it. And then it was only in this Zoom conversation with her that I had later on that she told me that, oh yeah, you've done a really a big size of that one. That's actually that was coasters for teacups. And yeah, it was just funny to see how like the whole meaning of the object was also like had dissolved in this process.
Because of scale. Yeah, one thing I didn't think actually is that the like 3D printing is really like all about form and not material. It's like emphasizing a lot of just the form over the material. Because if you looked at these objects from a material standpoint, they're all the same. They all have the same physical qualities. I mean, maybe the structure makes them more or less resistant, but they're basically all the same material. But they all, so it's all about surface and scale. Yeah, how scale and material change properties is quite interesting. This is pretty on scale, but
that was
but also like this kind of thing, it doesn't have the holes, so it would be not functional, right? So it's like
this kind of connection between material and information, that is one of the things that I was very interested in Catherine Hale's and her writing about it. And she traces the idea that information can be separated from a material back to the cybernetic movement. So I thought that was very, I mean, she is someone who has been connected in a way to the machine vision project that you're part of. And been involved with some seminars and given some lectures there that I've attended. And I found her writing on that and tracing that back to the history of cybernetics very very interesting.
She also writes about cognition, which is like related to Parisis as well.
Well, maybe we should just wrap up here. Thank you so much, Gabriele.
Thank you.
So generous and very, very interesting to hear you talk about this and to really how you consider like the things that I've worked with
and fun
and our conversations. That was I appreciate that.
I appreciate the invitation. Thank you.
Thank you for coming.
Thanks.